Integer tiles are great because it's really a hands-on way to see the patterns for adding and subtracting integers. So today, again, we just work with addition because if you really understand addition well, subtraction is a cinch. So this was your slate or our field. This is kind of the charge particle scientific idea of integers. And right now the box is empty, so if I had to give it a numerical value, I would say it's 0. Well, if I have a positive particle, like a proton, combined with a negative particle in science, like an electron, they neutralize and cancel each other out. So this would make a neutron because it's got a neutral charge. So how is this equal to 0? Well, this is a positive and negative is like a 0, and that's a 0, and that's a 0, and 3 zeros is equal to 0. I can also look at it as 1, 2, 3 positives plus 1, 2, 3 negatives. And if you remember, positive 3 and negative 3 are opposites, and opposites always have a sum of 0. So that's what we talked about next. This is just the property of opposites. So another reason this makes 0 is I've got the same number of positive charges as negative charges, so they're opposites. And that equals 0. So then I said, what's the value of my box now? So we started with just all these positives and negatives all over the place. There were 7 positives and 3 negatives. So a way to visually see that that equals a positive 4 is to circle all of the zeros and just literally take them out. So if I just picture taking this out of the box, and what I'm left with is 1, 2, 3, 4 positives. So it's just the particle integer tile method. And again, here I have a bunch of zeros, and I ended up with 5 more negatives than 0. So the answer is just negative 5. And then we found different ways of representing the number positive 5. So you guys couldn't start with just 5. You had to stick in extra pieces. So some people put in 7 positives and 2 negatives, and when you take out your zeros, the resulting value is 5. And then negative 5. Well, some of you had different amounts of zeros. This would be 9 negatives plus 4 positives, which gives me a negative 5. And as long as I just match up my positives and negatives and take my zeros out, whatever I have left over that doesn't have a match to make it a 0 is the resulting value of my whole what's on your slate, my whole field here, and that would be negative 5. And then you got to show another way of 5 that was different. Again, the same idea. I can put in as many positives and negatives as long as when I take out all those zeros, I have 5 extra positives. And the same thing with negative. I needed 5 extra negatives to make negative 5, so you can put in as many zeros as you want, and it still has the same value in the end. Okay, the putting together model for addition. So we started with 4 negatives in the box. And if I want to add a negative 3, all I do is put in 3 more negatives and then just count the result. The result is negative 7. I don't have any zeros in there, so I just have a negative 7. And the same as if I start with positives. If I have 4 to start with, and then I combine with that, or I put in 3 more positives, my result is positive 7. Pretty simple. Now if I put a positive and a negative, so here I started with 1, 2, 3, 4 positives. I combine with that 3 negatives, and when I take out my zeros, I've got 3 zeros right here. Take them out, I'm left with just a positive 1. So the answer is just 1. Then I gave you lots of problems. You had to model them on your slates, and so these were all the ones. So what you guys basically did here was you put in 3 negatives and 2 more negatives, and you had negative 5. And you put in 3 negatives and 2 positives, and you lined up your zeros, and the result is negative 1. And here we had 5 positives and 6 negatives. Take out your zeros, and the answer is negative 1. And here we just had all positives. 3 and 2 positives makes positive 5. And negative 7 plus a positive 3, we take out our zeros, and we have 4 extra negatives. And then we talked about the absolute value. In this problem, for example, what has the bigger absolute value, the 3 or the negative 7? Well, the absolute value of 3 is 3 because it's 3 units from 0, and the absolute value of negative 7 is 7 because it's 7 units from 0. So that means I'm going to end up on the negative side. So whatever number has the bigger absolute value, you keep the sign of that number. Or you can just think of money. If my debt is bigger than the money I have in my pocket, then my answer has to be a debt, which is negative. Or now you can add to that the tiles. If I put more negatives in my field than positives, then I have to, once I take out the zeros, have negatives left over. So that's just another way, another model to think about this. So we have the slide model along a number line, the money model with money in your pocket versus a debt. A debt's negative and the money in your pocket's positive. And now the integer tile model, which relates all of this math to science, the idea of positives, protons, negatives, electrons, and a positive and a negative canceling each other out with a neutral charge. So these two relate to science. And remember, mathematics is the language of science, so that's pretty cool. Okay, then we used it, so you had to write this situation as an addition problem. So the temperature outside started at 11 degrees in the morning. It dropped 3 degrees by noon, so we're adding a drop of 3 degrees, and then it rose another 4 degrees by late afternoon. So what we did is we looked at different ways to actually simplify this expression. Well, we know that order of operations, this is all addition, so it says we should add from left to right. So if we go left to right, 11 and a negative 3 is 8, and 8 and 4 is 12. So we're sure the answer is a positive 12. Well, we tried an experiment. We used some parentheses, and we can change the order in which the addition is done. And what we're looking for is, does the order matter? Well, this is a little different from the commutative property because we're actually putting in brackets. So I'm going to associate my 11 with my negative 3 first, and then add 4, and we put brackets or parentheses to show I want you to do that first. And then in my second example, I'm going to associate my negative 3 with 4 first, get that answer, and then add 11. And what we wanted to see was, do you get the same answer? Does it matter if I associate my 11 with negative 3 first or my 4 with negative 3 first? And what we found is that it did not matter, because this is 8 and 8 and 4 is 12. This is 1 and 1 and 11 is 12. So the order doesn't matter, which is pretty cool because that leads us to another property. Way back in 1835, there was an Irish mathematician, Sir William Hamilton, and he decided to call this pattern the associative property. And why did he call it that? Well, because if I associate these two numbers together first by putting them in parentheses, or I associate the 4 with the negative 3 first by putting them in parentheses, and then do the remaining addition, it doesn't change the answer. Another way to think of it is associations are groups, and parentheses are grouping symbols. So the associative property of addition says I can move my grouping symbols, my brackets, as long as the entire problem is addition, and it will not change the answer. I'll get the same answer. So again, the order with brackets does not matter, just like the order without brackets does not matter for addition. So we use this property to rearrange any addition problem, and you can use a combination. So first we use the commutative property to rearrange the problems, and we decided to put together all the negatives and put together all the positives, and then we use the associative property by putting brackets around all the negatives and brackets around the positives and looking for some compatible numbers. And then we found the answer to the negatives and the answer to the positives, and we added those two last. So in the brackets here, we end up with negative 100 and negative 25 and negative 75. These two numbers are very compatible because they make a negative 100, which is easy to put together with another negative 100. So that result is negative 200 in those brackets. And then the 52 and the 48 are compatible. They go together nicely because they make a nice even 100. And 10 more is 110. And this is like my slide model. If I slide to the left 200 and then to the right 110, I never cross over 0, so I end up at negative 90. Or with money, if I owe you 200 euro and only have 110 euro, I cannot fully pay you off. So I give you my 110 and I end up owing you 90 euro. Or with integer tiles, if I put 200 negatives in, 110 positives in, I'm going to have 110 zeros. When I take them out, I have 90 negatives left inside my field. So any one of those models will give you the same result of negative 90. Okay, you did this one with a partner, and some of you regrouped them. You use the associative and the commutative property. You switch the order and the brackets, and you put the two negatives together and the two positives together. And then you got from here, you got down to here with 50 plus, and this sum, and you got the total of a negative 112. I know what we did. We ended up doing it two different ways here. I wanted to show you didn't have to group these together. A lot of you group these together first, which was fine, and you still got 112. But then another way to group them is to put your 8 and 42 together, and that gives us 50, and then put the negative 75 in brackets with the 50, and that's negative 25, and then add your negative 87, and we get negative 112. So either way works as long as you're just rearranging and putting the brackets in. Now you can also use positive and negative numbers for rotations, and a rotation is simply a turn, and a turn is just rotating something from the center of a circle. You can use a protractor to measure these degrees, and the only thing you need to know is that the direction is important. So if I'm going to the counterclockwise direction, it's a positive number. So this is a quarter of a circle. Notice the right angle. So that's a positive 90 degrees. So I use a positive number for going counterclockwise. And this is a negative 90 degrees. I'm moving my heart from here to here. I'm rotating this around the center, and I'm going in a clockwise direction. So clockwise is a negative number. So these are quarter turns because they're a quarter of a circle. 4 90s makes 360, and that's a full circle. So remember, as a figure turns, it's rotating around a center. And we looked at the clock, and in 1 hour, the hour hand rotates one full circle. And it goes clockwise because that's where the word clockwise comes from. So that's a total of negative 360 degrees. One full circle clockwise. So the measure of the degrees an object is rotated is called its magnitude. And magnitude also includes the direction of the turn. So rather than using these big old long words like counterclockwise and clockwise, it's a lot simpler just to use a negative number when it's clockwise and a positive number when it's counterclockwise. And I don't know the history of this, but counterclockwise has just traditionally been given the positive magnitude. And it seems backwards to me. It seems like clockwise should be positive and counter should be negative, but it's the opposite of that. So just remember, we're dealing with opposites here, so it's the opposite of what you would think. So counterclockwise is a positive number. Clockwise is negative. Okay, so actually everybody stood up and you faced the clock, and we practiced rotating your bodies several times, clockwise and counterclockwise. And then how do you use this stuff? Well, Ramesh turned the faucet 80 degrees to get warm water, but then he noticed it was just way too hot. So he adjusted the temperature by turning the faucet negative 20 degrees. And the question is, what was the resulting turn in degrees? So we just drew a picture here. So if we just start with a ray facing north, remember my positive magnitude is counterclockwise. So this green arrow represents a turn of the handle 80 degrees. We just estimated our 80 degrees. And that's where it was too hot. And then a clockwise degree turn is a negative, so we're going to go back 20 degrees. We went to the left 80, we're going to go to the right 20, and the question is, what's the resulting turn? So what's this amount right here from where I started and where I ended? So it's really 80 plus a negative 20, which is 60 degrees. So now my handle is from here to here, which is just a 60 degrees, and it's counterclockwise, so it's positive. Really, you're just adding 80 and negative 20, just like we did before. A different example, Ron turned the faucet 90 degrees to get warm water, but he noticed it was too hot. He adjusted the temperature by turning his faucet negative 30 degrees. And what was the resulting turn? So I just called on a person at random and had them come up and sketch. So here was their starting ray. So first thing that, I think it was Brody did this one. I can't remember now. But anyway, in period 6, I think it was Brody. So he started by rotating at 95 degrees, which is counterclockwise. And then he went back clockwise, negative 30. And you can just see the difference. 95 minus 30, or 95 plus a negative 30, is 65 degrees for the turn. And the sketch just helps you picture what you're doing. And then you have some homework practice. So keep calm and don't waste water. And you can find this screencast on Moodle.